What's up, everybody? Welcome back to another video lesson. Today we're going to talk about something called the ideal gas law. Now, in a previous video lesson, we learned about the combined gas law, where if we take P1 and V1 over N1 and T1 and set that equal to P2, V2, N2, T2, then we can solve for a missing variable, assuming we know the other variables. But the ideal gas law is used when, let's just say I want to just know what the volume is of a sample of gas. Or what if I just want to know what the pressure is? I'm not going to change anything about the sample of gas. I just want to know a missing variable if I know the other ones. And since I have all the variables except for one, I can just simply solve for the missing variable. It's similar to the combined gas law, but it's a little bit different. We know that P1 V1 over N1 times T1 equals a constant value. And if I rearrange this so that the N1 and the T1 are on the other side, well, what I get is this relationship here. This means that the pressure and volume are proportional to the number of moles and the temperature of the gas. Proportional is not the same as an equality. They are not equal to each other, they're proportional to each other. But a way to make something proportional turn into an equality is insert a constant. And that is what is known as the ideal gas constant, or R. And as soon as you put an R in, this turns from a proportion to an equality. Now, we're going to talk more about what R is here. Now, R is what is known as the ideal gas constant, capital R. It is equal to a number, which is a multiplier, but this multiplier has 4 units. These are not variables that you plug in. These are units. It's a 4-unit number. It's got liters times atmospheres over moles times Kelvin. And it's important to note that the moles and the Kelvin are in the denominator together, and they're multiplied together. And so when you do an ideal gas law problem, we'll do some examples here in the next couple slides. But when you plug this whole number, including all 4 units, and the units matter, you plug them into R, and then you'll have all the things you need except for one of these variables, and you'll just solve for the missing variable. So in summary, the combined gas law is used when conditions are changing. When we know how it starts and how it ends, we can solve for one of the other variables. But if conditions aren't changing, as long as we know all except one of the variables, we can solve for that missing variable. And that is when we would use the ideal gas law. The ideal gas law goes by an affectionate name in the chemistry community. It's called PIVNERT. It stands for pressure times volume equals number of moles times R times T, PIVNERT. Now, the labels are really important when you're setting up problems involving PIVNERT or the ideal gas law. Now, first of all, pressure could be in atmospheres or kilopascals, and that's important, and you want to make note of that whenever you're setting up a problem, because the R constant is going to be dependent on which pressure unit you use. See down here, the R constant changes. This first one has atmospheres in it, where the second one has kilopascals in it, and the number changes because of that. So if you're going to have pressure in atmospheres, make sure you match the R constant that has atmospheres as well, where kilopascals match the kilopascals. Now, volume is always in liters. Number of moles is, well, a number of moles. And as we talked about in a previous video lesson, temperature should always be in Kelvin. And as a reminder, to take degrees Celsius and turn it to Kelvin, you add 273. So once you set up all the numbers that you know into PIVNERT, then you simply rearrange using algebra to solve for the missing variable. And the beauty of this all is that the R constant is going to supply all the units that are going to cancel out except for the one that you're solving for. And that's the purpose. The R constant has 2 purposes. 1, it's a multiplier. And 2, it provides all of the units in the problem, all of which will cancel out except 1, which will be the final label of your answer. Now let's do a couple practice problems. Now, this is a typical ideal gas law problem, and one of the things I like to do is I like to set up my variables, PV, nRT, over here down the left, and I like to label everything with its units so I know what I have. Now, in this problem, it's asking for what's the pressure, so that's my unknown. I'll call that X. Next, my V is 355 milliliter container, but I need that to be in liters, so I move the decimal over 3 to the left. It's 0.355 liters. Next, my N, well, I don't have N, but I have grams. And grams is easily converted to moles using the molar mass of CO2. And so I take the 0.25 grams and I divide 1 mole on top and 44.01, which is the molar mass of CO2. And I get a moles of 0.00568 moles. rounded off to 3 significant figures, and that is number of moles. Now the R constant I'm going to use here, well, it depends on what one I want to do. If I want my answer to be an ATM, then I'm going to use the one that is 0.08206 liters times atmospheres over moles times Kelvin. And that's the one I'm going to use because it doesn't say what the pressure needs to be expressed in, it just says what's the pressure. Finally, the temperature here is 35 degrees Celsius, but remember I need to add 273 to that in order to get in Kelvin, and that would be 308 Kelvin here down at the bottom. Now I set these up equal to each other. I do the P times the V equals nRT, and I do some basic algebra and I solve. So I'm going to divide 0.355 on both sides to isolate x, and once I punch that in my calculator, I'm going to get an answer of 0.400 atmospheres. And if you notice, everything in the units from the R constant cancel each other out. See, liters cancels liters, Kelvin cancels Kelvin, moles cancels moles, and the only one that isn't canceled out is the ATM, and that's my final answer, 0.400 atmospheres, rounded off to 3 significant figures. Now let's tackle this last one before we go. Once again, I'm going to use PivNert. I'm going to write down all the variables that I know and leave out the ones that I don't know and solve for the missing variable. This question says, what mass of sulfur dioxide gas is in 3.55 liter container with a pressure of 3,500, now that decimal point makes that 0 significant, 3,500 kPa and a temperature of 293 Kelvin. Now in PivNert, N means moles. We don't have moles in this problem. We've got the pressure, the volume, and the temperature, but we don't have moles. But if we find moles, then we can convert to mass, once again using the molar mass. So be careful. Sometimes we solve for moles, but sometimes we solve for mass, which is just moles converted to mass using the molar mass. So writing down my PivNert variables, pressure equals 3,500 kPa, volume equals 3.55 liters. My N is what I'm trying to find. The R constant this time is 8.314 liters times kPa over moles times Kelvin, and my temperature is 293 Kelvin. Now when I set up the PivNert, I'm going to use 3,500 kPa times 3.55 liters and set that equal to x times 8.314 liters times kPa over moles times Kelvin times 293 Kelvin. And this time I'm going to isolate x. So I'm going to take 8.314 and divide it on both sides, and I'm going to take 293 and divide it on both sides so I can get x all by itself here on the right. And when I punch all these into my calculator, I get x is equal to 5.10 moles of sulfur dioxide gas. That's SO2, so moles of SO2. Now I'm not finished with the problem because I've got to take the 5.10 moles of SO2 and I need to find the molar mass. 1 mole of SO2 is on the bottom. The molar mass of SO2 is 64.058 grams. And now all I need to do is multiply the molar mass times 5.10 and I get a final answer of 327 grams of SO2. It's worth noting that when I take this number and multiply it by the molar mass, I may write only 3 significant figures down here on the paper, but I actually take the whole number in my calculator and multiply it by 64.058. I only want to round one time, and I want to round one time at the end, and this is good proper technique when doing calculations and rounding significant figures. You don't want to round multiple times. So I might write 3 significant figures for the moles, but I know that I'm going to use the whole number from my calculator in order to do this final step, multiply by the molar mass, and only round to 3 significant figures the one time. So my final answer is 327 grams of SO2. Now PivNert includes moles as part of the calculation, but it's not stoichiometry. Well, not yet. And as you'd probably expect, if there's something that involves moles, we're probably going to introduce stoichiometry in this process as well. And that is certainly something we're going to do at a later date and time. But for now, that takes care of this video lesson. Thanks for watching.